Welcome to EDU World Space.
So we know from this problem that the material that's used in the wiring is copper. And we're also given a table of copper wires of different gauges, and there's a corresponding diameter that's associated with each gauge and a maximum current. And in part A, we're asked to determine what considerations determine the maximum current carrying capacity of these wires. So actually, it's the power which determines the current carrying capacity, because the power is what's being dissipated in the wire. And when there's a certain power dissipated, there's a certain temperature that's associated with it. So if it's too high, it can cause issues with your wire. And the power is equal to the current times the potential difference. So obviously the current plays a role, the potential difference plays a role. There's also I squared R, and R is equal to the resistivity times the length times the cross-sectional area, which is the resistivity times the length over pi over 4 d squared. So clearly the diameter of the wire also plays a role in determining the power. So these are the things that one must consider for a current carrying wire. Now, part B, we are asked to find the thinnest possible wire that we can use when we have a power of 4,200 watts and the wire is connected across a potential difference of 120 volts. So from here, we're given a power and a potential difference, and we need to find the diameter. So what we can do is use P is equal to IV, right? And then we know P and we know V. And if we find the current, then we can use the table to determine which diameter corresponds to this particular current. So we have the current is now equals to the power over the potential difference, which is 4,200 watts over 120 volts. And that gives us 35 amperes. And if we look at the table, we see that the 10 gauge wire can only carry a maximum of 30 watts, so we can't use that wire. And the gauge, if we go to a higher diameter, so the 8 gauge wire, that can carry a maximum current of 40. So it's the 8 gauge wire, or the diameter of 0.326 millimeters. And now let's get a new page to answer part C. In part C, we're to suppose that the wire used in this house is of the gauge found in part B. So the 8 gauge wire, and it has a total length of 42 meters. At what rate is energy dissipated in the wire? So basically, what is the power for this particular wire? So here we can use P is equal to I squared R, because we know the length will come in through the resistance. Recall that resistance is rho L over A, which is equal to rho is the resistivity. You can find that in table 25.1. And we're given the length, and then I'm just going to go ahead and write the cross-sectional area here in terms of the diameter. So and now we can go ahead and put in all the things that we know. So we want to find the power. We just found the current, which was 35 amperes squared, and now we'll substitute this expression for the resistance. So we'll take all of this and substitute it here. So the resistivity of copper is 1.72 times 10 to the minus 8 ohm meters. And the length we're given is 42 meters. And this I have to divide by pi over 4. And the diameter we determined in the previous problem was 0.00326 meters squared. And this gives us 106 watts. And now we've solved this, so let's go on to part D of the problem. Okay. In part D, we're told the house is built in a community where the consumer cost of electrical energy is 11 cents per kilowatt hour. If the house were built with wire of the next larger diameter than that found in part B, what would be the savings in electricity cost in 1 year? And we are to assume that the appliances are kept on for an average of 12 hours a day. Okay, so the diameter of the previous problem was 0.326 millimeters, and the new diameter, so this was the old one, and the new one, it should be the one up from that, which is 0.412 millimeters. And we got this right from the table. And we're asked to find what the power is given this new diameter. Not the power, but the cost of electricity given this new diameter. So the way to approach this problem is to actually find the power, and then so we're going to find P, and then we're going to use that energy is power times time. And then to figure out the cost, then we're going to multiply this by the cost of, let's say this is whatever the cost of electricity is times the electrical energy, and this is the answer we'll seek. So let's start by finding the power. So it'll be identical. We'll use an identical approach to the one in part C. So the power is equal to 35 amperes squared times 1.72 times 10 to the minus 8 ohm meter times 42 meters divided by pi over 4, but this time we'll use the new diameter, right? So that's 0.412. That should be millimeters, sorry. Millimeters. So (1.2) times 10 to the minus 3 meters squared. And this is equal to 66 watts. Okay, so let's get to the next page so we can have some room to work. So we know that the energy is equal to power times time. But what we're asked is how much money you would save if you use the two different gauges. So what is the difference between the energy consumption at a particular cost of energy between the two gauges of wire? So we can basically do something like here, just calculate the difference in the energy, which would be the power for the. So let me just give the gauge. So let P8, which is the 8 gauge wire, which is the one we found. And then and the next gauge was P6, right? So this corresponds to the diameter of 0.326, and this corresponds to the diameter of 0.412. And this is multiplied by the time. So, and the time we're told is 1 year, but the bulbs or the wire, the appliances are only on about 12 hours a day. So we can convert this into hours. So we should convert the time from 1 year at 12 appliance being used at 12 hours per day into hours. So this will be P8 minus P6 times 365 days per year. And they're on 12 hours per day. So it'll tell us how many hours they're on in the year. And this should be actually multiplied by 1 year right over here, so that our units are in hours. And this we found in part C, which is 106 watts, and this we found in part D, which is 66 watts. So now what we can do is I'd forgotten to multiply by, sorry, there's no T there. So now we can give a number. So we have this 106 watts minus 66 watts times the 365 days per year times the 12 hours per day. And this is equal to 175 kilowatt hour. And then if we multiply this by the cost, which we're given is 11 cents, then CE times delta UE is equal to $19.25.